And so you mentioned that right now you're really focused on quantum gravity. Can you tell us what that is?
So I'd like to say that like this, there's a problem of quantum gravity, and this is that we have two less fundamental physical theories. General relativity is Einstein's theory of gravity on the one hand, developed in 1915, 1916, and then we have quantum theory on the other hand, developed by a whole bunch of people, including Einstein, but also Heisenberg, Schrödinger, many others, developed in the mid-1920s. And those two theories are both very successful, predictably, where they apply, but they don't fit together. They don't fit together mathematically. They don't fit together conceptually. Really, it seems there ought to be a kind of unity in nature. We should really only have one theory that describes all of nature. So if we have two different theories describing different parts of nature, that isn't a satisfactory situation. So the problem of quantum gravity is to find a new theory, and probably a deeper, more fundamental theory, which approximates to general relativity on the one hand, in situations where that theory has been experimentally confirmed, and approximates to quantum theory on the other hand, in situations where that theory has been experimentally confirmed.
So when I was preparing some notes for this conversation, I wrote down only one sentence that had a big box around it in big block letters, and it said, "The problem with quantum gravity," because it seems like that's a very big problem. Why is it so difficult to reconcile quantum mechanics with general relativity?
Yeah, I don't know. If I knew the answer to that question, I would have done it already. I mean, it's taken, it's 100 years or so now since the problem has been around.
I'm not placing all the blame on you
No,
personally
it really is my
for
fault.
not having
I
done
have
it
not
yet.
done it so far. Yeah, I don't know. What I think is happening is that I think we're just not asking the right questions. We're not thinking in the right way. If you look at historically other situations, like after Newton developed his theory of gravity, his theory, universal theory of gravity, he wrote down this equation, and he didn't like it because it had instantaneous action at a distance, like I mentioned, and there was no substance mediating that force. And so he did the natural thing. He tried to invent a sort of a mechanism by which the gravity could, gravity could act like that. So two masses that are far apart could influence each other. And not just him, other people also tried to think of. They were called, mechanical ether models. So mechanical models that you could use to explain how gravity worked. These models were, amazing. They were quite detailed. And people spent a lot of time doing calculations and sometimes successfully reproducing the equations of Newton's equation of gravity. For example, Newton himself had this idea that the force that caused planets to be attracted to one another was the same as the force that causes aeroplanes to fly. So in some sense, he anticipated the work of Bernoulli, which came about 50 years later. If you have an airplane wing, then the speed at which the air particles go underneath the wing is faster than at which they go over the wing. And if the speed is reduced, if the particles go faster, then they don't hit the wing as often, so there's a lower pressure, and so that puts a force on the wing and makes the plane go up. And Newton had this idea, already back then, and he thought he could come up with some mechanism which explained gravity. René Descartes had this idea about vortices, very detailed models. There were many interesting characters, and that seems to be a lot of what people were doing. We're trying to come up with mechanical models to explain gravity. And then even later, with electromagnetism, when Maxwell himself actually used a mechanical model to derive his equations of electromagnetism. So people were just trying to explain things in terms of the concepts they understood, in terms of the concepts they were familiar with, and everyone was familiar with stuff, stuff pushing on stuff. That's a familiar concept. And so I think that's where we are now. We're bringing to bear on the problem of quantum gravity the ideas that we understand, and and it's probably just not sufficient. We probably have to find a way to think beyond that, or to somehow get out of ourselves and look at the problem from a different point of view. It's pretty difficult. It turns out to be very difficult.
I think it's really a unique challenge in this field, right? Because you really, from what you're describing, you really need to find a way to think in a different way and not rely too much on something that you already understand. Whereas in other fields of research, we would be trying to build on things that we already understand or look at consequences of things that we already understand. And whereas you have to probably keep reminding yourself, don't think too much about those things that you already understand. Try to think in a new way. So how do you train yourself to be in a kind of state of mind where that new way of thinking is possible?
Yeah, that's a good question. I mean, you could imagine developing a sort of systematic approach to that sort of thing, that you could perhaps follow sort of lateral thinking techniques, or who knows, some sort of meditative approach. I don't do that especially. I think I just sort of throw myself in every day and try to think of new ideas. Yeah, I don't have a good answer to that question, but I think it's a question that people should think about. What are the methodological tools you should bring to bear on physics? I've even asked philosophers. Philosophers spend a lot of time looking at physics and often speak about the work after it's been done. But philosophers could position themselves in such a way as to attempt to provide working physicists with methodological tools. How do you go about, well, in this case, for example, finding a deeper, more fundamental theory when you have two less fundamental theories? That seems like a fantastic philosophical question. Even if you don't actually construct the theory, just what are the methodological approaches to solving that kind of problem? Mm-hmm. But philosophers haven't really worked on that as far as I'm aware. So yeah, it's a fantastic question. I don't know the answer to it, but I think we should think about it.
That's great, yeah. And just as a follow-up to that, I'm just curious if, there was a satisfying solution of quantum gravity that was proposed in the near future, either by you or someone else, so that you needed to go think about some research in another field. Would you want to look at the consequences of this solution of quantum gravity, or would you want to find a new area of physics where you need to find another more fundamental theory, because that's kind of the way of thinking that you're trained in?
Oh, right. So that's a good question too. I mean, if you look at, you contrast Newton and Einstein, the two people I keep confusing. Newton spent a lot of time, doing calculations and being very careful about what his theory really predicted, his theory of gravity. And Einstein has been criticized for not doing enough of that in the case of general relativity. And there was kind of a lull in general relativity, and then some years later, people took up the cause again and did all these amazing calculations. So I hope in that particular case I would be more following in along this sort of Newton type approach. Yeah, it's difficult to anticipate in advance.
Yeah.
The challenge that you're working on, it seems like there's a parallel to 100 years ago, in the sense that there's these aren't quite working out, and then the model is made. How are you trying to build a model of, or a version of quantum gravity that overcomes some of these challenges, the disparate differences between quantum mechanics and general relativity?
So you mentioned that parallel with the problem 100 years ago that was solved by Einstein when he combined Newton's theory of gravity with his theory of special relativity, which included Maxwell's equations as a sort of an example. So I take that parallel very, very seriously. And if you look at what Einstein did, how did Einstein go about solving that problem? How did he go about coming up with the theory of general relativity? Well, he had to go through a number of steps, but his starting point was what he called the happiest thought of his life, which was when he came up with the principle of equivalence. And the principle of equivalence is really just this. If you imagine having a box, and it could be an elevator, and you have a person inside it and some objects, and that box could be falling under gravity, so it's high up and it starts falling, or it could be floating out in space. And imagine there's no windows, so the person inside has no idea which of the two situations they're in. So I suppose they'd be screaming. But aside from that, they would be in the case where the box is falling, everything would be falling at the same rate, and so it would feel like it was floating around. It would feel like they were floating out in space. And so Einstein said these two situations are equivalent, and that was the starting point. And then that idea gets turned into some beautiful mathematics, and he ends up incorporating geometric ideas that he learned from Minkowski, and also from his childhood friend Marcel Grossmann. Grossmann was a mathematician who knew about the sort of field of differential geometry, which went back to the mid 1800s. So there was lots of steps. It took him from 1907, when he had this happiest thought of his life about the elevator, until 1915, when he finally wrote down the correct field equations.
And how did he know in 1907, when he had this thought, that it was definitely an important ingredient in formulating GR? It still took him 8 years to finish, so I'm just curious.
Yeah, it's a great question. I mean, I'm not enough of a historian of science to know exactly what his thinking was around that, but you can see, looking at the idea, that it has lots of promise. Suddenly, previously we thought of gravity as a force. So Newton's first law says that a body will continue at a state of rest or in a constant speed in a straight line until it, in essence, acted upon by an external force. And gravity was regarded as an external force. So under gravity, a body wouldn't go in a straight line; it would go along a curve. And that was okay because gravity was regarded as an external force. And suddenly Einstein saw a way to stop thinking of gravity as a force at all, and think of it as more to do with the geometry. So a particle would actually be going sort of in a straight line once you're in this falling frame of reference. I mean, for a while. The principle of equivalence only applies in small boxes over small periods of time. So he must have seen that and realized he was onto something big. I can see that would have been the case.
Mm-hmm.